the next thing we're going to talk about is symmetry of function. So symmetry is important to understand, especially when you're going to graph it. It actually helps you do things faster if you know the symmetry of a function. Helps you find the shape of the graph a little better, and if it has matching extrema. Alright, so there's going to be two types of extrema we're going to look at. We're going to look at if there's symmetry, two types of symmetry we're going to look at. We're going to look at if there's symmetry with respect to the y-axis. Alright, so that means if I can fold my graph over the y-axis, it looks exactly the same. So there's no change when it's reflected across the y-axis. The picture is exactly the same even if we reflect it, use our transformation of reflection over the y-axis. There's no change to my function. It means if I fold it over the y-axis, it's exactly the same on both sides. Then there's the symmetry with respect to the origin. The origin's the 0, 0 on my xy plane. And so this means that there's no change when I reflect it across both axes. So I reflect it across both the x and the y. Alright, so both reflections would take place. But when both reflections take place, the graph stays the same. Alright, and what happens about the origin, it actually is a 360-degree rotation. So the shape's the same in opposite quadrants. Alright, so that's what it would be. The shape would be the same in opposite. So quadrant 1 and quadrant 3 would have the same shape. Quadrant 2 and quadrant 4 would have the same shape, the way it reflects. And so what happens is it actually has to do with even and odd functions. Even functions have one type of symmetry, odd functions have another type of symmetry. Alright, so even and odds, I'm going to start with even. So even's the easier case. Alright, so even and odd function, it's even if it's the first type of symmetry. So a function is even if for every number in its domain, alright, when I plug negative x in, right, negative x is when I flip it over the y-axis, right, that's that transformation of flipping it over the y-axis, the function doesn't change. And the reason why it's called even symmetry is because what's happening here is your powers are even, right? When I square something, it doesn't matter, right? If I plug 2 in and I square it, it's 4. If I plug negative 2 in, I square it, it's 4. And so when my powers, my degrees are even, if all of my degrees are even, it has this even symmetry where it's symmetrical about the y-axis. And so again, if I plug in negative numbers, it's exactly the same as when I plug in positive numbers. All right, I get the same function value out. All right, so my function f of x is even if and only if, wherever there's a point positive x, y on the graph, there is a same point at the negative x. So negative x and the same y value on the graph. Right, the graph is folded along the y-axis. The left and right sides match exactly. So it's symmetric about the y-axis. We call them even functions because it's even degrees that get me there. All right, so some examples, so pictures down here are examples. All three of these functions have even symmetry. These all have even symmetry. All right, they follow that idea. So if I pick a point here, so this is a point on this graph, that's the point 2, 3. Well, there's a matching pair on the other side at negative 2, 3. And so if I picked any function value over here, x, y, I get a matching one on the other side at the negative x. Same y. All right, that's what it means to have even symmetry. I fold it over the y-axis and it's identical. All right, the function values are identical. It's found at opposite x values, but the function values are identical. The second function here does the exact same thing, right? My second function, if I fold it over my y-axis, it's got symmetry. If I pick a point on this side, it's got a matching point on the other side, right? That's 1, 2. On the other side, it's negative 1, 2. Same pair. Same thing for the next function, all right? It's got symmetry over here. If I take this W shape, it has a matching pair. So this point on here was 2, 8. Well, it's got the matching point on the other side, would be at negative 2, 8. All right, so it matches on both sides. All right, so that's even symmetry. And so I'm actually going to look at these and then determine their local and absolute extrema as well. All right, so the first one, so I'm going to call this graph 1. right? It's even symmetry. It does have a absolute minimum of -1. No absolute max and no local extrema. Alright, so graph 1, that was graph 1. Graph 1, no local extrema. Alright, graph 2 has a maximum, right? This would be the maximum at 1, 2, 3, 4, 0, 4. And so graph 2, I'm going to write my answers down here, has an absolute max of 4, no minimum, absolute minimum, and no local extrema. Alright, so graph 2. Absolute max of 4, no absolute minimum, no localized extrema. Alright, so this one's going to be my graph 3. All of them have even symmetry. Alright, my last graph, so graph 3, has a absolute max of 8, right? It just happens at 2 locations. There's 2 matching points, but both of them have the value 8. And so it just happens at 2 and -2. And so this one has an absolute max of 8. It just located twice. No absolute minimum, but it does have a local min. Alright, the local min is this point here, which is at 0, 6. So local min of 6, right? Its minimum's the 6. And it's localized, right? It's at that local little valley there. Alright, so, and no local max. Alright, so it's a local min, an absolute max, no absolute min, and no localized max. Alright? So that's even symmetry. And then practicing our max and mins again. Next one is going to be the odd symmetry. Alright, so and I always find the odd symmetry the harder one, at least for me, to wrap my brain around. Again, we're reflecting twice, is what we're doing. And so when we have odd symmetry, it's reflected over the x and then reflected over the y, and when I do that, I get back to the exact same value. And so when I've got odd symmetry, I plug in the -x, and if I plug in the -x, my function's the exact opposite of what my original one was. And the reason it's odd is because this happens with odd degrees, right? When I plug in a negative number, I get a negative number out for an odd degree, right? If I take -2 cubed, I get -8. So that's what's happening here with the odd degrees. I plug in my negatives, and I get out a negative. I plug in positives, and I get out a positive. Alright, and so my function when it's got, and so my degrees are odd, right? I have odd degrees for this to happen. And so I have matching values, but they're opposites. So my function has odd symmetry if and only if, whenever I have the point xy, I also have the exact opposite point. So if I've got 2, 3, my function also has the point -2, -3. Right, the exact opposite. It's an odd function. We call it odd because that's what the degrees are. The degrees are odd degrees, like cubes or fifth degrees or those types of things. And what would happen is when you rotate it, it rotates around the origin 180 degrees. Alright, a half turn. That's what a half turn means. So you take the original graph, rotate it 180 degrees, a half turn, and then you get the exact same shape. Alright, so these are examples of all odd degree functions. So if you look here, if I took this shape and I rotated around, so the matches are in the opposite quadrant. Right? If I took quadrant 2, flipped it over the origin, it's exactly the same as quadrant 3. So the same thing's all these. Quadrant 2, flip it over, it's the same as quadrant 3. If I take quadrant 2, flip it over, I get quadrant 4. And again, I'm flipping it over the origin. The check is that I've got points that are the opposite, right? Exact opposite. So this point was 1, 1. On the other side, I should get negative 1, and that's true. So if I take any point in this line, I've got x, y, I should get the exact same matching values, just the opposite. Okay, so if I've got 2, 8, on the other side I should have negative 2, negative 8. And where this helps us out a lot of times is finding, if I find one extrema, so this example, they told me that this extrema was at 2.13. Well, knowing that this has odd symmetry, well, I should have a matching point on the other side that the exact opposite is. Negative 2.1, negative 3 would match with that on the other side because it's got odd symmetry. Right? Odd symmetry. You could check using another point. Right? This would be the point 2, 0. Well, I should have a matching point on the other side, and I do. Negative 2, 0 is its matching point. Right? Odd symmetry. Right? Again, usually it's a cube. Both of those look like they're cube shapes. Right, the last one is also the same. Right, it's got odd symmetry. If I pick a point here, which again I'm going to pick the maximum, that looks like it's at 1.5, 1. So 1.51. It should have a matching negative 1.5, negative 1, and on the other side, and it does, right? It matches. They're the exact opposite. That's what makes it odd functions. So I'm going to do the same thing with this one as I did before. I'm going to label this graph 1, graph 2, graph 3, and so those are my odd functions. And I'm going to find their local and absolute extrema. Alright, so for the first one, the answer is none. Alright, there is no extrema, either localized or absolute. There are no peaks and valleys there. So 1 has no extreme. The answer is none. 0 extrema. Alright, graph 2 has no absolutes, right? Because I'm shooting off to negative infinity there, positive infinity there. But it does have 2 localized extrema. It has a local max, right? That's its local max of 3, and a local min of negative 3. And whenever you have odd symmetry, that's always going to happen. Right? There's always going to be the exact same max and min, but in the opposite sign. So if you've got a maximum of 3, you should have a minimum of negative 3 due to the nature of odd symmetry. Right, so the same thing's actually going to happen in graph 3. No absolute extrema, because I'm shooting off to negative infinity and positive infinity. But I do have local. I have a local max of 1. And a local min of negative 1. And again, due to the nature of odd symmetry, that's what happens with local max and mins. They have a local max on opposite sides. So if I've got a maximum of 2 and it's odd symmetry, I should have a minimum of negative 2 with the way odd symmetry works. Alright, we will stop there. Oh, I'm going to go, yeah, we'll stop there and we'll pick up the next part, the theorem, in the next, and determining even and oddness in the next set of notes.